Yeah, that clock keeps ticking till we start up in here. Yeah, that clock keeps ticking till we start up in here. If you came to learn chemistry, you did your part. Time is ticking down, so just be ready, cause it's about to start. When we solving for problems, we solve it information. You know Ben's Chem videos will provide you with equations. Never have to stop and think about it, this the station that will provide you with the chemistry all in relation. If you came to learn chemistry, you did your part.
Hello everyone, and welcome to the Ben's Chem Videos Sunday night live stream. Tonight, we are going to continue as we dig deeper and deeper into our discussion on thermodynamics. Very fun, very exciting stuff. Very excited to talk to you about these things. So without further ado, I present to you Thermodynamics Volume 3. As always, your feedback is more than welcome and highly encouraged, so please feel free to drop your thoughts in the chat if you're watching this live, and if you're watching this as a video, please feel free to leave me a comment, because without your feedback, I am completely and totally lost. All right, so we are going to kick things off by reviewing the content from Volume 2, the last Thermodynamics live stream in this series. By the way, if you want to watch Volumes 1, 2, or 3 by the time that this is produced, you are more than welcome to look at my Thermodynamics live streams playlist. There's a link right down there in the description. So, okay, back to Volume 2. So in Volume 2, we were basically talking a little bit more about entropy, right? Entropy, that's that thermodynamic property that is associated with disorder, with randomness, and with energy dispersal. And one of the things that we mentioned in Volume 2 is that entropy is the driving force for physical and chemical change. So any physical or chemical change that you see around you, and all of the ones that you're not seeing, all of those are driven by disorder and randomness. They are all driven by entropy, which is kind of interesting, but true as far as we currently understand it. So one of the things that we were talking about with entropy is what happens to the entropy of a sample of matter as it changes its state. So things like melting, freezing, vaporization, condensation, sublimation, deposition, all of those so-called phase changes. What happens to the entropy of a sample of matter if, let's say, I take a glass of water and I throw it in the freezer and freeze it? What happens to the entropy of that water as it freezes from a liquid to solid? And basically what we said was that anytime you're going from an arrangement of molecules that is highly orderly to an arrangement of molecules that is more disorderly, then the entropy would increase. In other words, your change in entropy, or your delta S, would be positive. And conversely, if you're going from something disorderly to something orderly, then the entropy would decrease. The change in entropy, or delta S, would be negative, right? So going back to that example of putting a glass of water in the freezer, well, you would have a fairly disorderly sample of matter, which is the glass of liquid water, where you have these molecules that can float around, they can rotate, they can slide past one another. Going from that to solid water, or ice, which is a much more orderly arrangement of those water molecules. They can't really move around one another. They can't really move past one another. They do vibrate a little bit, but their locations with respect to one another are relatively fixed. That would be a decrease in entropy associated with such a process, because you're going from, again, disorderly to orderly. So that's entropy and changes in state, pretty straightforward. We also talked about entropy and gas phase reactions. So anytime you have a reaction taking place in which your reactants and your products are both gases, then what happens to the change in entropy during a gas phase reaction? Well, the answer is if you produce more moles of gas than you started with, then the entropy will increase. In other words, if there are more moles of gas in the product side of that chemical equation than there are in the reactant side of that chemical equation, then entropy will increase if you produce more moles of gas. Conversely, if you produce less moles of gas, in other words, if your products have fewer moles of gas than your reactants do, then entropy would decrease. So that's pretty straightforward also. And that led us into a formal definition of the second law of thermodynamics, and I've put it in bold here because it's really important. And the second law of thermodynamics, remember, that says that for any spontaneous process, the entropy of the universe increases. For any spontaneous process, the entropy of the universe increases. So that means that the second law of thermodynamics is really huge, because it actually predicts the direction of the flow of energy. So one of the things that I sort of forgot to demonstrate in Volume 2, I meant to, I had everything set up, but I just completely forgot to do. So imagine what happens if you take, let's say, an ice cube, right? So I have an ice cube here. Let's say you have an ice cube and you drop it in water. What happens? What happens when you drop an ice cube in water? Well, energy in the form of heat will flow from the water to the ice, which will make the water get a little bit cooler and the ice get a little bit warmer until eventually thermal equilibrium has been established. Now, what if it was possible to have energy flowing in the opposite direction? In other words, what if energy flowed from the ice to the water, which actually made the water warmer and the ice colder? The first law of thermodynamics wouldn't prevent such an energy transaction from occurring so long as the total energy of the universe is constant. Energy is neither created nor destroyed. That's the first law of thermodynamics. But the reason why energy doesn't flow from the ice to the water and why it always flows from the water to the ice or from the warmer object to the colder object is because that type of change would violate the second law of thermodynamics. So if energy flowed from the ice to the water, then that would not result in an increase in the entropy of the universe, and so therefore it never ever happens. Anything that happens, any spontaneous process, the entropy of the universe must increase, right? And so we talked about that, and we also talked about the fact that sometimes we see processes that happen spontaneously in which entropy seems to decrease. And the example that I used is if you have a lake in a very, very cold part of the planet in the wintertime and the whole lake freezes over, well, how is that increasing the entropy of the universe? I mean, after all, you had an orderly arrangement of water molecules that froze into you had a disorderly arrangement of water molecules in a lake that froze into a very orderly arrangement of water molecules in a frozen lake. So how does that increase entropy? And the answer is, well, remember, the criterion for spontaneity is not the entropy of the system, but the entropy of the universe. So remember, the universe in any thermodynamic situation is composed of two components: the system, which is the part of the universe that we're studying, and the surroundings, which is everything else. So if you look at a lake that has frozen and you take the lake to be your system, certainly if the lake has frozen, that means the entropy of that system has decreased. But remember, the entropy of the universe must increase in order for a process to be spontaneous. So as long as the entropy of the surroundings increases by a larger amount than the decrease in entropy of the system, then delta S for the universe can be overall positive, and you can have an overall spontaneous process, which is exactly what happens when a lake freezes over when it's very, very cold. But if it's very, very warm, then lakes don't freeze over. So that leads us into the next bullet point here, which is the temperature dependence of delta S, or the change in entropy for your surroundings, right? The change in entropy for your surroundings depends highly upon temperature. Why? Well, think about the origin of the entropy of the surroundings. How exactly does that increase if you have, say, water freezing? Well, remember, water freezing, that is an exothermic process. It actually increases, it releases heat into the surroundings under conditions of constant pressure, right? So because freezing is exothermic, that release in heat into the surroundings is going to increase the entropy of the surroundings. But the degree to which the entropy of the surroundings is increased as a result of heat being released by the system into the surroundings depends on temperature. Because if you release some heat into surroundings that are already quite hot, then you're not going to have much of an effect upon the entropy of the surroundings. On the flip side, if you release some heat into surroundings that are very, very cold, well, then that little amount of heat that you added is actually going to have a much more profound effect. It's going to increase the entropy of the surroundings much more. So again, the entropy, change in entropy of the surroundings depends on temperature. And we also talked about how to quantify the entropy change for the surroundings, and that can seem like a pretty daunting task, like it's pretty difficult to do. Like, how do you measure the entropy of literally everything else in the universe, right? Well, it turns out that we were able to derive an expression for delta S surroundings by focusing solely on the system. And we were able to derive this equation down here on the bottom right, which says that the entropy change of the surroundings is equal to the negative of the enthalpy change, the delta H value of the system, divided by the temperature. Now, just a word of caution, this equation down here only works under conditions of constant temperature and constant pressure, right? So that is basically where we left off. Now, let's get to the topic of tonight's stream. Tonight, we will be talking about another very important, very useful thermodynamic property called Gibbs free energy. Gibbs free energy. So this is a very, very important, like I said, very, very useful thermodynamic property. This isn't something that we're just going to learn about and then we can just forget about it. No, this is going to pop up over and over and over again as we continue to discuss thermodynamics. So this gentleman on your right, this is Josiah Willard Gibbs. He was born in 1839, died in 1903. So in terms of like human history, this guy was active, less than 150 years ago. So, in terms of human history, it's actually pretty recent. He came up with these concepts and these developments. And so this property, Gibbs free energy, that we're going to talk about is named after him. So what I'd like to do is I'd like to take you guys on a little journey to the whiteboard, and we are going to derive the expression for Gibbs free energy. So I'm going to go ahead and start with the formal definition of Gibbs free energy. So Gibbs free energy is symbolized by a capital G, right? G for Gibbs free energy, go figure. And Gibbs free energy formally is equal to the enthalpy, H, minus the product of the temperature and the entropy of a system. So G is equal to H minus TS. So we're going to sort of keep this in mind in the back of our heads as we sort of derive our way to the expression for Gibbs free energy, and just to begin to understand how important it is and how we can connect it to the entropy change of the universe, which is the criteria for spontaneity. So going back to the equation that we looked at previously when it comes to the entropy change for the universe, right? That is as follows, where we have delta S for the universe, UNIV, right, is equal to the sum of delta S, the entropy change of the system, and the entropy change, the delta S value for the surroundings, right? Delta S universe equals delta S system plus delta S surroundings. And we also learned back in volume 2 that under conditions of constant temperature and pressure, that the delta S surroundings term is equal to the negative of delta H of the system divided by the temperature, right? So this delta S surroundings term is equal to this term right here. So all I'm going to do here at this part of the derivation is I'm just going to substitute. So wherever I see delta S surroundings, I'm going to insert this minus delta H system over T and see if we can't get anywhere. And so the result of that little substitution is the following, where we have delta S for the universe, the entropy change of the universe, is equal to the entropy change for the system minus delta H for that system over T. So again, all I've done here is I've taken delta S surroundings and I've swapped it out with minus delta H system over T. So hopefully we are all still following here, because we're going to continue. So now I'm going to do something else. I'm going to actually take this entire equation and I'm going to multiply it by minus T. I'm going to multiply this whole equation by minus T, and hopefully it will make sense later on why I'm multiplying this entire equation by minus T. I know it seems like kind of random, like who would ever think to do that, but trust me, it should make some sense here in a little bit. So, whoops, I didn't mean to move that. Let me see if I can just shrink this down a little bit, create myself a little bit more room, right? So I'm going to multiply this whole equation by minus T. So what is that going to look like? Well, if we do the left-hand side of the equation, we're going to end up with minus T delta S for the universe is equal to minus T delta S for the system. And then if we multiply negative delta H system over T times minus T, that's basically going to cancel out the T's, right? That T is going to cancel with that T, and we'll end up with plus delta H for the system, right? So minus T delta S for the universe is equal to minus T delta S system plus delta H for that system. And it's much easier to have just something minus something than negative something plus something. So I'm just going to move this around a little bit, if you don't mind. So what I'm going to do, I'm just going to get rid of that plus, right? And I'll move this out of the way, and I'll take this and throw it over here, and I'll grab you, and I'll bring you back here. And so let me clean this minus sign up a little bit, because it might be a little confusing. And so we have derived our way to this equation right here, where we have minus T delta S for the universe is equal to delta H for the system minus T delta S for that system. Now, at this point forward, what I'm going to do is I'm going to drop the subscript SYS, right? I'm going to drop the subscript SYS, and I'm just going to assume that we are talking about the system. So from now on in this derivation, whenever I see delta H and whenever I see delta S, I'm talking about delta H of the system, and I'm talking about delta S of the system. And so we end up with minus T delta S for the universe is equal to delta H minus T delta S. Now, this is starting to look pretty close to the formal definition of Gibbs free energy, right? G equals H minus T S, right? And so if I wanted, let's say, if I wanted delta G, I'll do this in purple over here. If I wanted delta G, that would simply be equal to delta H minus T delta S. And again, we're assuming in this situation that T is constant, so that's why there's no delta T, because we're assuming that this is taking place over conditions of constant temperature, right? And so here we see that the right-hand side of both of these equations are identical, right? Delta H minus T delta S here, delta H minus T delta S over here, which really means that your delta G value, your change in Gibbs free energy, is equal to minus T delta S for the universe. So again, the reason why this property is so useful is because it allows us to predict the direction of spontaneity by focusing solely on the system. We don't have to try to measure something for the surroundings. We can put all of our focus on the system and develop a criterion for spontaneity that way. And so you can see here that this equation, how this works, right? So Gibbs free energy, or the change of Gibbs free energy, is proportional to the negative of the entropy change for the universe. And so just as the entropy change for the universe is the criteria for spontaneity, delta G is also a criteria for spontaneity, although opposite in sign. So instead of delta G being positive, delta G is negative for a spontaneous process, right? So I think this might be a good thing for me to write up here somewhere, right? So let me see if I can just shrink this down once more and give myself a little bit more room here. So if delta G is greater than 0, in other words, if it's positive, then this would be a non-spontaneous process. I'll just say non-spawn because I don't have enough room to write the whole word non-spontaneous, right? And on the flip side, if delta G is less than 0, in other words, if delta G is negative, then this is a spontaneous process, or just spawn for short, right? So just as the sign of delta S needs to be positive for a process to be spontaneous, delta S of the universe, the sign of delta G needs to be negative for a process to be spontaneous, right? And so if we take this equation here, it's too bad I already highlighted this because I wanted to use it again. So basically, okay, so what I'm going to do is I'm going to rewrite this equation because we're going to use it in the slides that follow. So I'm going to just take everything here in this derivation and say goodbye to it. And I'm just going to rewrite that equation for delta G up at the top because like I said, we're going to be using it over and over again. So I want to write it like nice and big, right? So it's delta G is equal to delta H minus T delta S. And remember, delta H and delta S, these are with respect to the system, right? So again, that's why it's so useful because we can predict the direction of spontaneity with properties that are only defined with respect to the system, right? So really, we have three sort of variables here. We have delta H, the change in enthalpy, right? We have delta S, the change in entropy, and delta H and delta S could both they could be either positive or negative, and we'll see what the signs of delta H and delta S, what effect that has on the possible sign of delta G, whether or not the reaction can be spontaneous, and under what temperatures it can be spontaneous or not. And then we have T, right? T, that's the temperature. It can't go negative because it's an absolute temperature. It's in kelvins. You can't have a negative Kelvin. So this is basically a positive constant right here. T is just a positive constant. It's a temperature. So basically what we're going to do is I'm going to take you guys back to the PowerPoint, and we're going to look at 4 possible cases, 4 situations in which we have different signs of delta H and delta S, and basically look at what effect this has upon the spontaneity of a process, looking at that expression for delta G, change in Gibbs free energy, that we just derived. So there's 4 cases. There's the first case up here on the top left, in which delta H is negative and delta S is positive. So you have an exothermic process with a positive entropy change for the system. The second case over here on the top right, that's when it's reversed, right? Delta H is positive, you have an endothermic reaction, and delta S is negative. And then these 2 below describe 2 cases in which delta H and delta S have the same sign, right? This one on the bottom left here is when delta H and delta S are both negative. And then finally, we have the situation in which delta H and delta S are both positive. So what effect do the signs of delta H and delta S have on the sign of delta G? What effect do the sign of delta H and delta S have on the spontaneity of a process? Got a message in the chat here from Angelina. It says, so to determine if a process is spontaneous, we can rely on delta G for the system or delta S for the universe. Just focus on delta G because it's evaluated more easily, focused on the system only. Yeah, that basically sums it up. Remember, because delta G is related to delta S for the universe, it's just that minus T is sort of that proportionality constant that connects them, right? So they're basically kind of the same property, but one just has that minus T factored into it, if that makes sense. So what I'm going to do is I'm going to take this back to the whiteboard for a second. So let's see if I can, I'll try to grab one of these images at a time and just like paste them into the whiteboard so that we can sort of all follow along here. So this is the first case, right, where delta H is negative and delta S is positive, right? We can call this case 1. So again, looking at this equation up here, delta G equals delta H minus T delta S. How are the signs of delta H being negative and delta S being positive going to affect the sign of delta G? Well, if delta H is negative, right, and delta S is positive, then this term over here, this minus T delta S term over here on the right, that's going to be negative, right? Because negative times positive is going to be equal to a negative, right? And so this whole term over here, this minus T delta S thing, that is also negative. So it doesn't matter in this case what your temperature is, right? The delta G, the sign of delta G is always going to be negative because you're combining 2 negative terms, right? And so delta G in this case, right, and this is when you have a exothermic process, negative delta H, and a positive delta S, delta G is going to be less than 0. It's going to be negative, and it's going to be negative at all temperatures, right? So any reaction in which delta H is negative and delta S is positive will always be spontaneous no matter what the temperature is, okay? So we went with that case. Let me just erase everything that's on the board right now except for this equation here, which I want to continue to use, and we're going to go to the next case, right? The next possible combination of signs of delta S and delta H. So let me grab that from the PowerPoint real quick, and I will paste it right into the whiteboard. So here we go. Okay, so this one is the case in which delta H is positive and delta S is negative. So what effect does that have on the sign of delta G? Okay, well, we'll do the same thing before. Just kind of look at the equation and figure it out, right? So delta H, if that is positive, right, and delta S, if that is negative, right, well, T delta S or minus T delta S, that's going to become a positive term because a negative times negative is positive, right? And so you're combining 2 positive terms together. I just realized that I'm kind of off the screen there. There we go. So yeah, if delta H is positive and this entire T delta S term is also positive, you're combining 2 positive terms, which means that your change in Gibbs free energy, your delta G, will be greater than 0. It'll be positive, and it'll be positive at all temperatures, because again, it doesn't matter how large or small the value of T is. Since both of these terms are positive, then your delta G has no choice but to be positive, if you want to think of it like that. So we're going to move on. So we've talked about the two cases in which the sign of delta H is different from the sign of delta S. Now we're going to move on and talk about the two cases in which the signs of delta H and delta S are equal. So let me go grab that from the PowerPoint real quick. Just going to copy and paste this in here. Should be, whoops, I accidentally minimized my, okay, here we go. All right. So let's look at the third case. This is the situation in which the sign of delta H and delta S are both negative, okay? Well, this is when it starts to get a little bit interesting, right? So if delta H is a negative term and delta S is also a negative term, if you have a negative times a negative, that's going to give you a positive term for that whole T delta S business. So you have something that's negative and you have something that is positive. So they're kind of like competing with one another, right? These two terms. And so it is entirely possible for delta G in this case to be positive or negative. It just all depends on the relative values of delta H, delta S, and T, right? Now let's imagine a situation in which the T is, I just realized I'm not on the page here. Let me try that again. So imagine a case where the T is, just say T is low, right? If we have a low temperature, right? Now, if our temperature is very, very low, that means the positive value of this entire term is going to be quite low. And the delta H here will sort of overcome that, the negative delta H. And so that'll result in a negative sign for delta G. So if the temperature is low, then that means your delta G is going to be less than 0. It'll be negative at low temperatures, right? But if the temperature is high, right, then it sort of flips, because this, if the temperature is high, then this positive term over here on the right, this T delta S business, becomes large, and to the point where it can sort of outcompete, it can overcome the negativeness, if you will, of that delta H. So that, there's a temperature at which this flips from spontaneous to non-spontaneous, right? And the delta G becomes positive, becomes greater than 0. So what basically, just to wrap up what we just looked at, is that if delta H is negative, in other words, you have something that's exothermic when you also have a negative value of delta S for that system, then at low temperatures, it'll be spontaneous. In other words, delta G will be negative, and at high temperatures, it'll be non-spontaneous, right? And there's a certain temperature at which it sort of flips from spontaneous to non-spontaneous based on the sign of delta G. So we're going to look at the last case, and then we're going to basically look at a problem in which we can sort of put this equation to work and see if we can figure out whether a reaction is spontaneous or non-spontaneous based on given values of delta H and delta S and T. So bear with me for just a moment while I erase the rest of this stuff. By the way, if anybody finds this stream valuable, I would appreciate your support in the form of leaving a like on this video. Leaving likes on videos might not mean much anymore, especially now that the public dislike count is gone, which is I think YouTube really messed up by doing that. I hope they listen to every creator I've talked to, every user I've talked to, almost everybody unanimously does not approve of their decision to remove the public dislike count. But I'm going to spare you the talk on that. I could talk about that for hours, but instead we're going to move on. So, all right, let me go to the PowerPoint real quick and show you the last thing here. Also, if you'd like to support the stream monetarily, you're more than welcome to send a super chat, or there's a link in the description that says support the streams. If you follow that, you can donate through PayPal if you want to help support the stream. Your donations are always welcome, and they are highly appreciated. So I don't know what's going on here with my mouse cursor. I'm just stalling while I try to figure this out. What the heck is going on? Why can't I see my mouse cursor? This is really weird. My program just completely hid my mouse cursor on me. I don't know what's going on. Okay, I think we still have what we need though, so I'm going to continue, hopefully. But if I can't see my mouse cursor, I don't know what I'm going to do here. Okay, all right, so if you have this situation in which delta H and delta S are both positive, well, what effect does that have on the spontaneity? What effect does that have on the sign of delta G? Remember, negative delta G, that means it's spontaneous. Positive delta G, that means it's non-spontaneous. So delta H, again, if that's a positive term, right, and delta S is also positive, then that means that this whole T delta S term is going to be negative. So it's kind of like the same situation as before, where whether this is spontaneous or not, it's going to depend upon the temperature, right? Now, what if the temperature is low? What if you have a low temperature? Well, if you have a low temperature, you're going to have this negative minus T delta S term over here, which is going to be a negative term, but if it's a low magnitude, then your delta G quite likely can end up being positive. So if your temperature is very, very low, that means delta G will be greater than 0, which means positive. And if it's positive, that means that you have a non-spontaneous process. I just realized I'm kind of off the screen here. There we go. All right, so, and then as a converse to that, if we have a high temperature, right, what's going to happen to delta G then? Well, in that case, this minus T delta S term, which is negative, becomes large in magnitude, and it's going to be larger in magnitude than this positive delta H term, and so in that case, your delta G would be negative. It'd be less than 0, and you would have a spontaneous reaction. So I'm going to take you guys right back to the PowerPoint where I've got a table ready to sort of summarize all the things that we just sort of looked at here. So let me go back into this, see if I can blow it up a little bit bigger. There we go. And I'm just going to get my big ugly head out of the way here. So this table basically just summarizes all of those relationships that we just sort of looked at, where we have a column for the sign of delta H, we have a column for sign of delta S, and again, delta H, the change in enthalpy, right? Delta S, the change in entropy, and both of these are with respect to the system. Again, that's why delta G is such a useful property, right? And basically, this just summarizes what we just talked about, right? If delta H is negative, delta S is positive, then we're going to have a negative delta G at all temperatures. This reaction is spontaneous at all temperatures. On the flip side, if we have positive delta H with negative delta S, then we're going to have a delta G that is positive at all temperatures, something that is non-spontaneous at all temperatures. And if delta H and delta S are both negative, well, delta G is going to depend on temperature, right? Low temperatures, you're going to have a negative delta G, spontaneous. At high temperatures, you're going to have a positive delta G, non-spontaneous. And then finally, the last one that we looked at, if delta H and delta S are both positive, then at low temperatures, delta G will be positive, non-spontaneous. And then finally, at high temperatures, delta G becomes negative, which means spontaneous. Now, if I were you, I would not try to study by memorizing this table. Instead, I would just understand that equation, delta G equals delta H minus T delta S, and then you can sort of reason your way through based on the mathematics of it all, like we just did, rather than having to like memorize this whole table, which I don't really recommend memorization. I recommend actually like learning the scientific principles and the equations that govern the relationships that you're talking about whenever possible. That's kind of one of my big tips, is to avoid memorization. All right, everyone. So last but not least, we are going to work through an example, a problem in which we put what we just learned about Gibbs free energy to work. And so that's going to begin right now. So once again, let me move my big old head out of the way there. Okay, I'm finally out of the way. All right, so it says to consider the following reaction where we have calcium and oxygen combined with one another to form calcium oxide. That's represented by this chemical equation here. And we are given the values of delta H and the values of delta and the value of delta S, right? It says that delta H is minus 1,269.8 kilojoules. And it says that delta S, the change in entropy, is minus 364.6 joules per Kelvin, right? So one's given in kilojoules, the other one's given in joules per Kelvin. So that's kind of important. The first part of the problem says to calculate delta G for this reaction at 25.00 degrees Celsius. And it asks us, is the reaction spontaneous at this temperature? And then the second part says, what temperature does the reaction change from spontaneous to non-spontaneous? So let me go ahead and just copy paste this problem here into the whiteboard. Shouldn't take me very long. So we are in the whiteboard now. Gonna delete all of that stuff and paste the problem in here. Okay, there is the problem. Okay. So without even using any equations, we can just simply look at the sign of delta H and delta S. We can see here that they're both negative. So that means that anytime delta H and delta S are the same sign, that means that the sign of delta G could be positive or it could be negative. It just all depends on the temperature, right? So I just lost my pen. I don't know what I did with it. This isn't good. The pen that I used to draw freehand on my whiteboard with, I don't know if I dropped it on my lap or what, but I need like a hey, be right back technical difficulties like screen that I could just go to when I do these streams, because definitely having some difficulties right now. What the hell did I do with that thing? Where is it? Yeah, I don't think I can actually bang this problem out without it, so it is very important that I find this thing. Oh, okay. Yep, it was in my lap the whole time. All right. We're back in business, people. Okay, so as I just said, the sign of delta H and delta S, they are both negative, so that means that this could be a negative delta G, spontaneous, could be positive delta G, non-spontaneous. It all just depends on the temperature. So if we take a look at the equation once again, so the equation is delta G is equal to delta H minus T delta S. Okay, now let's go ahead and define all of our terms here, right? So our delta H, that was given, that is equal to negative 1269.8 kilojoules, right? So that's our delta H, that was given. Our value of delta S, what was that? Well, that is minus 364.6, and that's joules per Kelvin. Right? Now, one thing that is immediately jumping out at me is that one of our properties is given in kilojoules, the other one is given in joules per Kelvin. Now, in order to use these units together, or in order to use these properties in the same equation, we need to make sure we have units that are compatible. And so we have a choice, right? We can either take our delta H value and convert it from kilojoules to joules, or we can take our delta S value and we can convert it from joules per Kelvin to kilojoules per Kelvin. It's just a matter of your personal preference. Personally, I would prefer to convert the delta S value to kilojoules per Kelvin, but again, there's more than one way to skin a cat, as they say. The choice is entirely yours. So I'm just going to convert this real quick. So I'm going to set up a conversion factor where we put joules at the bottom and kilojoules on the top. Of course, there are 1,000 joules in 1 kilojoule. Make sure that units cancel. So joules cancel with joules, which means we're going to end up with kilojoules per Kelvin for this unit of delta S. So that's going to be minus 364.6 divided by 1,000. So that's going to be minus 0.3646. And let me see if I can give myself a little bit more room here to sneak in that unit. That's going to be kilojoules per Kelvin. Okay, so we have our delta H and delta S, and they are in compatible units. And then we have T, right? Temperature, right? That's given. That's 25.00 degrees Celsius. And just as a general rule of thumb, anytime you are given a temperature and you want to use it in any kind of thermodynamic equation, thermodynamic equations are written to include absolute temperatures, not relative temperatures, which means that we need to take this 25.00 degrees Celsius and we need to convert it into kelvins. How do you go from degrees Celsius to Kelvin? Well, it's simple. All you do is you add 273.15. So whatever the degrees Celsius temperature is, you add 273.15 to it, and you will get the temperature in kelvins. So if I have 25.00 degrees Celsius and I add 273.15, what I end up with for the temperature is 298.15 kelvins. All right, so we have our delta H, we have our delta S, we have our T, and we have converted everything that we need to into units that will actually work with this equation. And so now we are ready to plug these values in, insert them into our formula for delta G, find delta G, and then determine based on the sign of delta G whether or not this reaction is spontaneous. If delta G is negative, then yes, it is spontaneous. If delta G is positive, no, it's not spontaneous. So let's go ahead and do that. Okay, so delta H is T, delta G is delta H minus T delta S. So that means that it's going to be, what's our delta H? It's minus 1269.8, and that's kilojoules, right? So that's our delta H, and then it's going to be minus the product of the temperature and the entropy change, which we have both of those. So the temperature, that's 298.15 kelvins, and the delta S value, that is negative 0.3646, and that's kilojoules per Kelvin, right? So this whole expression, if you have a good scientific calculator, you can just type this entire expression into your calculator, which is what I would recommend, which is what I'm actually about to do in a second here. So let's make sure our units cancel. So we're going to have Kelvin canceling with Kelvin, and we'll be left with just kilojoules, right? We'll have kilojoules minus kilojoules, right? So let me type this into my calculator real quick. By the way, if anybody watching would like to follow along and you have your own scientific calculator, I would highly encourage you to do that, because it's entirely possible that I make a mistake here. So if you'll give me just a moment, I'll type this into my calculator, and hopefully if anybody wants to follow along, hopefully we both get the same thing. Otherwise, one of us messed up, and I hope that that's not me. So negative 1269.8. Let's see, that's going to be minus 298.15 times negative 0.3646. And the value that I got was, let's see if I can squeak it in down here, negative 1,161. That doesn't look very good. Let me try that again. 1,161, and that's kilojoules. That's the unit, right? Negative 1,161 kilojoules. That is our Gibbs free energy change for this reaction based on the given values of delta H, delta S, and the temperature. So then the question becomes, is this reaction spontaneous? Well, since delta G is negative, then yeah, you betcha. This is a spontaneous reaction. If delta G were positive, then it wouldn't be spontaneous. See how easy that works? All right, so we've just figured that out. So that answers question A, right? We calculated delta G. We determined that, yes, it is spontaneous because we have a negative value for delta G. And so that moves us right along to the next part, part B, which says, what temperature does the reaction change from spontaneous to non-spontaneous, right? So basically, there's going to be a transition point. There's going to be some temperature at which it flips, right? From spontaneous to non-spontaneous. So how do we figure that out? And the answer is actually pretty easy. So bear with me just for a second while I erase all the stuff that we kind of... Actually, you know what? I don't want to erase all of that. How can I... Oh, no. Oh, wait. Okay. Let me selectively erase what I want to get rid of, and then we can go from there. Just a moment. Bear with me. That's T. Okay, so in order to figure out what temperature this reaction changes from spontaneous to non-spontaneous, it's actually pretty simple, right? If the reaction changes from spontaneous to non-spontaneous, that means the sign of delta G flips from negative to positive. So what we're really looking for is the point at which delta G becomes 0, right? So all we have to do here is just set delta G equal to 0 and then solve for the T value, right? And so we can do a little bit of algebra here, right? So we have, let's say we subtract delta H from both sides of this equation. That'll give minus T delta S is equal to minus delta H. Multiplying this equation by -1 simply gives it T delta S is equal to delta H. Positive T delta S is equal to positive delta H. And then finally, dividing by delta S on both sides gives T, right? Because these delta S's cancel. So that's going to give us T, I'll just rewrite it over here, is equal to delta H over delta S. So now all we have to do, now that we have our expression for T, is to insert the values of delta H and delta S into this equation, solve for our temperature. It's going to be reported in kelvins, but that'll give us the temperature nonetheless. So delta H over delta S, right? Got another message in the chat. It says, if temperature changes, though, we're no longer under standard conditions. Shouldn't we use the other... So shouldn't we use the other formula which accounts for that? Yeah, that's a good question. We're we're getting a little bit ahead of ourselves here. I definitely do want to introduce that very equation that you're talking about later on. For the time being, we're talking about conditions of constant temperature and constant pressure. But yes, you are correct. The mathematics does become more advanced when you start to account for non-standard conditions in which your temperature is not constant. And if you ever move on to take physical chemistry, then you'll learn all about that using things like differential equations, partial derivatives, and all that kind of stuff. The math becomes very much more complicated when you start dealing with non-ideal conditions and non-constant temperature variable temperature processes and stuff like that. But for now, we're just keeping it simple so that we can gently introduce the content, right? So basically, what did we do here? Just to answer that question of when does this reaction go from spontaneous to non-spontaneous, or what temperature does this reaction go from spontaneous to non-spontaneous, you just set delta G equal to 0, algebraically solve for T, which we just did. We have the expression right here. Now all we have to do is just plug and chug, plug those numbers in. So delta H over delta S, the value for delta H, that's minus 1,269.8 kilojoules, right? That's going to be divided by our delta S. Our delta S, it's going to be minus 0.3646 kilojoules per Kelvin. And so we can see here that kilojoules canceled with kilojoules, will be left with Kelvin. That's doesn't really look much like a K, but it's supposed to be a K. I apologize for my abysmal handwriting. That looks more like a K right there. And so now, again, I invite anybody who's watching to plug this into your scientific calculator, see if you get the same thing that I do, and let's see what the answer is. So negative 1,269.8 divided by negative 0.3646, and I guess that's going to be kept to 4 significant figures. And I'm going to just go ahead and erase this stuff over here. And that's going to give us a value of 3,483, and that's going to be kelvins. 3,483 kelvins, right? So that is the temperature that's sort of like the pivot point, right? So what did we say earlier? We said that if you have both negative delta S and delta H, at low temperatures, it'll be spontaneous. At high temperatures, it'll be non-spontaneous, right? So this is sort of that threshold in temperature. Any temperature under this, it's going to be non-spontaneous. Any temperature, oh wait, let me back up on that one. Any temperature below this, it'll be spontaneous. Any temperature above that, it'll be non-spontaneous. So that is how this equation works, and that just was one example of how you can put this equation to work. And let me just write the equation one more time, just because it is so important. It is delta G is equal to delta H minus T delta S. And again, delta H, delta S, those are both with respect to the system. And again, I know I've said it many times in the stream before, but that's the reason why delta G is such a valuable property, is because it allows us to predict the direction of spontaneity, whether or not something will be spontaneous, by talking about thermodynamic properties that are exclusive to the, or that are solely measured from the system. And that's a very advantageous place to be in as a chemist or as a student. All right, everybody. So that is it for me. Sorry that I didn't mean that audio to continue like that. I'm still working out this this whole streaming software. But that's going to be it, everybody. Thank you very, very much for watching. Like I said at the beginning, your feedback is very, very important to me. That's why, Angelina, you the only one who was actually submitting any chat messages. I salute you. Thank you for your participation and in this discussion. And I would invite anybody at any of my streams, which they always are on Sunday nights, 9 o'clock p.m. Eastern time, to come on in and actually have a back and forth discussion. So important that I get your feedback. I need to know if what I'm doing is helpful or if it's just a waste of everybody's time, because I don't want to waste your time and I certainly don't want to waste mine. So, all right, everybody, that's going to do it for me. Like I said, I stream Sunday nights, 9 o'clock p.m. Eastern time. Next week, what's that going to be on my calendar? What is it? Today's the 5th, so that means next week is the 12th, December 12th. That will be the next live stream. I really, really hope and look forward to seeing you guys there. So, all right, take care.